In our last video, we looked at the continuously compound interest formula, A equals PE to the RT. And what we're going to see in this, in this video is that can be used, this formula can be used as any kind of an exponential growth or decay model. And we'll talk in a minute more about what I mean by decay model. So remember when we had a linear model, that was f of x equals mx plus b. When we had a quadratic model, that was f of x equals ax squared plus bx plus c, and so on. So what we're looking at here is the exponential model. So if I start with a certain amount of something, we're going to call that p sub 0 with a subscript of 0 here. And that means the amount of whatever it is that we're measuring, the population or the money or the Krypton 85, which we're going to look at in a few minutes, etc. It's the amount at time 0. That's where the little subscript of 0 comes from. That's your initial amount, what you start with. So we see that that's the same thing as the P in this formula. The amount that you have after time t has gone by, P of t, is your future value, your A, in this formula. E is just the number E, that's not going to change. R is going to be your growth or decay rate. And we'll talk again in a minute more about how I know if I have growth or decay rate. And that's going to be written as a decimal. And then the T is still time. And usually time is going to be years, but time could be a much smaller increment. For instance, if you were talking about a population of fruit flies, you could be talking about time after a certain number of hours or a certain number of days. So we're going to see that this formula can be written using these 4 variables as a function. P of t equals P sub 0 e to the kt. And this is going to be our exponential model. How we can express exponential growth or exponential decay using a function. Now, remember, if we graph an exponential function, we know our basic exponential shape is going to be a curve like this. If we were to reflect that curve over the y-axis and just reflect the whole curve right over that axis, we're going to have a graph that looks like that. Notice on this one, we're growing over time. On this one, we're decreasing over time. This is what's known as a decay model, and this is a growth model. Now remember what causes a reflection over the y-axis, and that is if you have a negative inside of the function. In other words, in the exponent. So we're going to see, to have the classic growth shape, k is going to be a positive number. And if k is negative, we'll have that reflection, and we will have decay, and it will be if we have a negative exponent. So you can tell immediately, if you're looking at an exponential model, you can tell if you will be growing over time or decaying over time, in other words, getting smaller over time, by whether the rate is a positive number or a negative number. Let's look at some examples of this. Let's say that I want to write an exponential model or an exponential function for the growth of a population T years after the year 2000 if the population was 50,381 in the year 2000, and the growth rate is 2.7%. All right, write an exponential model for the growth of a population T years after 2000, the year 2000, if the population was 50,381 people, I guess we need units on here, in 2000, and the growth rate is 2.7%. Now let's think about what this question is asking us to do. It's asking us to write an exponential model. So what this is asking us for is a function that is an exponential function. So anytime I know that I'm dealing with an exponential model, I am trying to find an exponential function of this form. This is our basic exponential model. The P of t is like the f of x. That's just going to say P of t. So I need to figure out what P sub 0 is, and I need to figure out what K is. E is just the number E, that won't change, and T is our variable, like X. Remember what P sub 0 means. It means the amount at time 0. If we look back in our problem, we see that in the year 2000, the population was 50,381. And notice that this says the population T years after 2000. So in 2000, we are at T equals 0. So this sentence right here is telling me that the population in the year T equals 0 is 50,381. In other words, P sub 0 equals 50,381. So P sub 0 is our starting amount, 50,381. So we can put that in for P sub 0 in our function. P of t is just the name of the function. P of t equals. The E is just the number E. K is given as 2.7%. And that tells me K, and because this is a growth rate, that's going to be a positive number, and I'm going to write it as a decimal. So K equals 0.027. So back here in my model, I can put in my 0.027 for K, and then T is just T, my variable. So this question asked for an exponential model, and this is my answer, my exponential model. Now let's look at using the exponential model to do some things. Let's see if we can figure out, using the model, what was the population in 2007. What was the population in 2007? What I know here is 2007. 2007 is 7 years past 2000, so I know t equals 7. And what it's asking me is, what is the population? So that's saying find P of t. In other words, evaluate P of 7 in the given formula. So I can plug that in my calculator using my E-caret key. So I have 50,381. Second ln on mine. You're just using E-caret. So I have E-caret, parenthesis, and then I put in 0.027 times 7, close parenthesis, enter. And I get 60,862.31. So in the year 2007, using this model, we'll have approximately, and I'm just going to go ahead and round this to the nearest person, we'll have approximately 60,862 people living in our town here. All right, what if I knew that when the population reached, say, 75,000, I would need to build another elementary school? And I want to know how long I would have to plan for that. And we're assuming that we're back in the year 2000. So let's say in the year 2000, we are in the year 2000, we have 50,381 people. We know that we're growing at the rate of 2.7%. And I want to know, when will the population reach 75,000 people? So on this one, we know we're still using our model, our growth model that we had found earlier. Now on this one, what we know is the future value, how many people. So that's telling me that we know that P of t is equal to 60,000, we know that my future value is what I'm trying to find here, 75,000. That's how many people P of t is equal to after time t. But what we don't know, what we're trying to find, when, is the time. So we're trying to find t, we know P of t. So if we plug those both into, we put both of those into the formula, the 75,000 replaces all of P of t. So we have 75,000 equals, and then the 50,381 is just part of my model, e to the 0.027, and t is my variable. T is what I'm trying to find. And hopefully by now, you've looked at all of our other videos. You've done the homework on solving exponential equations, on using the natural logarithm to do so, and you can solve this equation yourself. So I want you to pause the video for a minute, solve this equation for t using the natural logarithm, and let's go ahead and round to the hundredths place, and then start the video back up. So we know that when we're solving for a variable in the exponent, we're going to divide both sides. And I'm going to keep several decimal places here. I could either leave it as a fraction, or I can write out all of my decimals here. And this is probably plenty. But I'm not just going to write 1.5 because that will give me rounding error. And I really need to be sure that I have a more accurate answer than that. Then I can take my natural logarithm on both sides. And remember, when I take the natural logarithm of e to that exponent, I just get the exponent. And then I can divide both sides. By 0.027. And I get t equals natural logarithm of 1.488656, close parenthesis, close parenthesis, divided by 0.027, enter, and I get, that's approximately equal to 14 point, and I have 736, and I'm rounding to the hundredths place, and 6 is more than 5, so I go up to 4, and my units are years. So it's going to take me approximately 14.74 years. So when it says, when will it reach 75,000 people, t equals 0 in 2000. So I see that I am going to get to 75,000 in about 3/4 of the way through 2014. So I'm just going to say that by 2015, I will have reached 75,000 people. So in this problem, we use exponential growth to write a model, and then we used it to do a couple of different things. What we're going to do here is I'm going to give you a problem, and this one's going to be exponential decay. And then we're going to look at doing the math with exponential decay, and we're going to see that it works exactly the same way. So let's say that we are going to look at krypton 85, which is an element, and it has a decay rate of 6.3% per year. And we're going to write an exponential decay model. If I start with $15 micrograms of krypton 85. Now, the 85 is part of the name of the krypton. It doesn't have anything to do with our model. So just ignore the 85 for our purposes here. What I want you to do is write an exponential decay model. So that's part A. Write an exponential decay model. Part B, I want you to find the amount of krypton 85 after 3 years. How many micrograms of krypton 85 would be remaining after 3 years? And finally, how long would it take to decay to 7.5 micrograms of krypton 85. So I want you to look back at the problem that we just did, write your model, use it to predict the amount of krypton 85 after 3 years, and then find how long would it take to decay to 7.5 micrograms. And I'm going to point something out here. This is important to remember, that we have a decay rate of 6.3. So that tells us that our K, our rate, is a negative number because we are decaying. So I want you to try and work out parts A, B, and C. Pause the video, work out those 3 parts, and then check back. All right, so we know we're writing an exponential model. So we have P of t equals P sub 0 e to the kt. In the problem, it tells me that P sub 0, the starting amount, is 15 micrograms. And it tells me that we have a decay rate of 6.3. So decay tells me it's negative 0.063. So when I write my model, P of t equals 15 e to the negative 0.063 t. So this is my answer for part A, the model. Part B, I want to find the amount of krypton 85 after 3 years. So it's saying t equals 3. So what I'm doing is I'm finding P of 3. So I plug a 3 in for t. And I plugged it in on my calculator. Don't forget my negative, which I did. So let me start over here. 15 e caret negative 0.063 times 3. And you have to use the negative at the bottom of the calculator, not the minus sign. It won't accept that. Enter. And I see that I have 12.42 micrograms of krypton 85. And then for part C, how long would it take? How long would it take? Is saying find T if P of T is equal to 7.5. So I am solving the equation 7.5 equals 15. Remember, the 15 is part of the model, so it's there every time. E to the negative 0.063 t. And notice this is a decay model, so the ending amount is less than the beginning amount. So I'm going to divide both sides by 15. 7.5 divided by 15. is 0.5 equals e to the negative 0.063 t. I can take the natural logarithm of both sides. It gives me the exponent because it's the same base. And then I can divide both sides. By negative 0.06 t, negative 0.063, and so t is approximately equal to 0.5 divided by negative 0.063, approximately equal to 11 years. All right, so what we've seen is how to write an exponential growth or decay model, and then how to use it to predict an amount in the future or to find the amount of time it takes to get to a specific amount. In our next lesson, we're going to look at a couple of special things called the doubling time and a half-life. And we're going to see that we're going to use the same model, but we don't need to know how much we started with and how much we ended up with. All we need to know is the ratio